2-7 parent functions and transformations. This lesson is all about how to understand basic graphs and then move them up, down, left, right, stretch them, shrink them, flip them, rotate them. This lesson we're going to go back to every single chapter because every time we learn a new graph, we're going to use the exact same rules to move them, to transform them. All these graphs we should already know. The constant functions, anytime y equals anything, just goes to that value and then draw a line straight across. Follow the tally mark. Identity function, it's y equals x. I should think of more of it as a linear, let's think about the linear function instead. Y equals mx plus b. And that's a transformation of the identity function, but that's what that is. Absolute value, we talked about the last lesson. Absolute value makes this part positive. It looks like a v. Quadratic might be a new one for you guys. We'll go in great detail next chapter, but quadratic function, it looks like a u. First step, identify the type of function. I like to say linear, but it's identity. And this is absolute value. Now, stuff's been happening to it, but it's an absolute value function. That's the parent graph. That's where we start off. This graph started off as this graph, and then we did stuff to it. We shrunk it and we stretched it a little bit. Let's start off with transformation. Transformations is how you move up, down, left, right. Anytime you get a basic graph, I want you to know two things. Here's the inside part of the function. The inside part of the function affects the x values. It's a short way for me to saying it affects it horizontally. X values move left and right. When I say the inside, you can move something left and right. And in this case, you do the opposite. Like you're solving it, it's x minus 4, you're actually going to solve it, and you get x plus 4. You do the opposite of what it says. For example, we did this last time. If I give you absolute value of x minus 3, this is on the inside. You do the opposite, it's a plus 3, which means you're going to move it right 3. We have a graph, move right 3, then we draw our absolute value function. That's what the inside does. Anything on the inside moves it left and right, we call that a horizontal translation. Anything on the outside, that affects the y value. If you look at the y values move up and down. So it's to move stuff up and down. Now, it doesn't have the same parentheses. On the outside, you just follow what it says. If it says move up, move up. If it says move down, move down. For example, if we give the absolute value of x plus 4, that's on the outside. We're going to move it up 4. That's what those basic transformations do. And this is key to all transformations. You got to remember that inside is the x values, which means you move left and right, and you do the opposite. Outside is the y values, which means you move up and down, and you follow what it says. Inside opposite, outside follow. Inside opposite, outside follow. Okay, let's practice a couple. Describe the translation instruction and graph the function. The first step is actually always identify what's on the inside and what's on the outside. Because if you do that, then we can follow inside x opposite, outside y follow. Look at these things. This one right here, that's the inside. Right, that's inside the function. Where if it was like this, that would be outside the function. On this one, that's outside the x squared. It's outside. The inside version would be something like this. That would be on the inside. Notice how it's inside the parentheses. Wherever there's parentheses, if it's inside the parentheses, inside. So here it's on inside, and it's inside x opposite. I'm going to treat it like a negative 3. And x means left and right. I'm going to go left 3. 1, 2, 3. And then I'm going to draw an absolute value graph. And we're just doing a sketch here. It's not a perfect graph. Just a sketch of what's supposed to be going on. Looks like that. If you have an x squared graph, an x squared graph looks like a u. And this is on the outside. Outside is y, follow. Y's go up and down. We're going to go down 4. So a graph, 1, 2, 3, 4. Then you draw a parabola. We're just doing a sketch. What it should look like. That's inside effect. Inside x opposite, outside y follow. That's how I move something up and down. And it doesn't have to be basic graphs. I can do this with anything. If I give you a graph like this, let's say f of x looks like this. Let me actually give points here. But this point right there is going to be negative 2 and 2. This is 1 and 4. And this is 1, 2, 3, 4, 5, and 4. I'm just saying f of x is that. Negative 2, 2, 1, 4, and 5, 4. If I say, hey, I want you to graph f of x minus 3. This is on the outside. Outside y follow. So that means we're going to move it up and down. We follow and move it down 3. The one thing you can do is get every single point, move it down 3. Get that point, down 3. Get this point, down 3. Get that point, move it down 3. And that's your new graph. Another thing you can do, though, is get the actual points. If you get your points here, which are negative 2 and 2, 1 and 4, 5 and 4. If you just subtract 3 from all the y values, you get the point negative 2, negative 1, 1, 1, and 5, 1. Look at the points I got. Negative 2 and negative 1, 1, 1, 5, 1. That way also works. Same idea. If I just give you a basic graph of points, you can either just do the same thing, move every single point down 3, or this actually do math. Subtract 3 from all the y values. You get the exact same answer. Next is let's talk about reflections. Reflections are when you flip your graph. Now this is supposed to be the first step. You're actually supposed to do reflections before you start moving stuff. So there's two types of reflections. Let's focus on the inside one first. Well, not like this. Notice how it's on the inside. Inside's x. Opposite follow doesn't really matter here because we're just flipping it. We're going to flip it across the x. We're going to flip it horizontally, left and right. I call this a horizontal flip because the x is horizontal. You're going to flip it left and right. Most books call this a y-axis flip because when you flip it left and right, you're flipping it across the y-axis. I think it's a little more confusing. I just like to say horizontal flip. Let's do a quick example. I'm just going to give you a basic graph. Let's say f of x looks like this. That's my f of x graph. And I'm going to say, let's graph f of negative x. You notice how it's on the inside? Inside's x. Move it a horizontal flip. Anytime you see a negative, it's a flip. We're going to flip it horizontally. We're going to flip it this way. If you flip it horizontally, it's going to be like right here. And you can go like that. Or you flip it across here. Horizontal flip. That's what the negative inside does. Flips it horizontally. The negative on the outside y. Y is up and down. So I call this a vertical flip. We're going to flip it up and down. Most books call this an x-axis flip for the same idea. So you flip it up and down, we're flipping it across the x-axis. For me, that's a little confusing. I prefer vertical flips. You flip it up and down. For example, we'll do the same graph. I have that graph right there. Let's draw my f of x. And then I want to draw negative f of x. Right, it's on the outside. Y, it's a vert flip. So we're going to flip it up and down. Vertical flip. This one looks like this. You flip it up and down. If you see a negative on the outside, you flip it up and down. You see a negative on the inside, you flip it left and right. So that's called a reflection. Let's do a couple quick examples. Looks like this. Look at the basic function. They call it the paired function. Looks like that. It's an absolute value graph. There's a negative on the outside. That means it's a vertical flip. We're going to flip it up and down. Something like this. Remember, we're just doing a sketch. That's a negative absolute value of x. Flip it up and down. Now this graph, there's two ways to do it. So you're saying, is that the inside or outside? Honestly, it doesn't matter. With the basic x, that's either one. It's an inside and an outside. There's no real inside or outside for a basic x. For that right there. Basic graph looks this. In this case, it's a rare case I counted either one. We'll flip it horizontally. Right, so you flip it this way, then you get a graph that looks like that. That goes down here, that goes up there. That's what looks, that's bad. That's even worse. I'm going to stop making it worse. I'm going to stop. Anyway, I wouldn't even do it that way. Ha. The way I would do this, linear graphs, don't even worry about it. Just do it with normal graphs. We know how to graph that. Starts at 0, slope of negative 1 over 1. Do it like a normal graph. How we know how to do it. Anyway, that's flips. Inside opposite, outside follow. Like before, I could do it with the basic graph. Let's say, I think this was negative 2 and 2. This is 1 and 4. We'll say 5 and 4. I'm going to do the exact same idea. I'm going to ask you to graph negative f of x. So in this case, one way to do it is you go, okay, it's on the outside. So that's y. So it's a vertical flip. Y tells me we go up and down. We're going to flip it up and down. But you flip it down, kind of like this. You can flip all those down there. So that's one way to do it. Other way to do it, like I said earlier, you can actually just do the math on it. What's going on here is this. You're multiplying your function by negative 1. If I get all my points, another way to do this is just multiply all your y values by negative 1. If I multiply my y by negative 1, I get negative 2, negative 2, 1, negative 4, and 5, negative 4. If I graph that, negative 2, negative 2, 1, negative 4, 5, negative 4. It works either way. That's the great thing about this. You could just do understanding the concept of, okay, I got to flip it up and down, so flip it down. Or you can do the math of it and just go, okay, I'm multiplying my graph by negative 1. Since on the outside, multiplying the y values by negative 1. You get your graph, multiply the y values by negative 1. Let's do the same thing for the inside function. If I was doing this the old-fashioned way, I go, okay, it's on the inside, x. That means I move it left and right. X means left and right. Horizontal flip. You're going to flip it over here. That goes right here. And that goes over there. Look at this. It's supposed to be straight. Not my best graph, but that's what it's supposed to look like. That's one way to do it. Another way of doing it is, well, on your x's, it's a little tough. Inside opposite, normally I'd say, oh, multiply by negative 1, but actually inside you do the opposite operation. We're going to divide by negative 1. It's a little tricky, but you divide by negative 1. Instead of multiplying my y by negative 1, we're going to divide our x by negative 1. All the x values, divide them by negative 1. And I get 2, 2. 1 divided by negative 1 is negative 1, 4. And we're only doing the x values, negative 5. 5 divided by negative 1 is negative 5, 4. If you look at my points, that's 2, 2. That's what I was going for there. Negative 1, 4, negative 1, 4, and negative 5, 4. There's always two ways to do it. You can always just understand the concept and go, okay, I got to flip it up and down. I got to flip it left and right. Or you can actually do the math. If it's on the outside, it affects the y values. Multiply your y by negative 1. Oh, it's on the inside, it affects your x value. Divide your x values by negative 1. The divide part's a little funky. Remember, inside opposite. Instead of multiplying, we're going to do the opposite operation. We're going to divide. Okay, so we got how to reflect it, how to flip it. We got how to move it up and down. Last part of transformations is how to stretch and shrink it. When there's a number on the outside, it's like the slope. That number is going to stretch or shrink something. Same thing when there's a number on the inside. And that's what we're going to focus less on in this class, but in general. When you multiply by a number, you're stretching or shrinking. You're making it bigger or smaller. How about the outside one first? Hopefully by now you can notice If it's on the outside, it's going to affect the y values. So right, and we follow. Outside y follow. So basically, we're going to multiply y values by a. The general idea is this. If a is bigger than 1, call that a stretch. It makes the numbers bigger. If a is less than 1, but bigger than 0, I don't really care about the sign. If I see like a -3, that means it's on flip. It doesn't do anything else to me. If it's a 3, it's a stretch. If it's a -3, it's a stretch with a flip. We only care about positive values. So it's a shrink. And honestly, the best way to show you this is I'm going to use the website Desmos right here. It's a nice free website. Start graphing. So let me show you, let's graph something. I'm going to go y equals x squared. Let me zoom in a little bit. Then I'm going to do another graph. Y equals 3x squared. You see that one? It's stretched it up. It's kind of like a slope. 1 you can go to 3. 1 goes all the way up to 3. Or normally it's 1, 1. It doesn't follow exactly. It does follow exactly when it's linear. Like an absolute value follows perfectly, but parabola is not actually a slope, but it's kind of like a slope. So 1, 1, and then 3x squared goes 1 to 3. You can see it stretched it up. If I get really high, if I go to 10, it's even more of a stretch. To me, at 1, it's going all the way to 10. After that, it doesn't really follow it, but that's the idea. 1, 5, 2. You can see the bigger the number I get, the closer to the y-axis it gets. If I put a negative in front of it, all it does is move it down. It doesn't do anything else besides flip it up. Now if I put a fraction, then it makes it wider, shrinks it down, squishes it down. If I put like a 10 down here, it makes it really wide. That's what an outside stretch shrink does. The bigger the number, the skinnier it gets because it goes up really fast. If I put 5 there, it gets skinny. The smaller the number, the wider it gets. That's a outside y shrink and stretch. On the inside x opposite, this is a little tougher. In this one, we multiply y values by a. In this one, we're going to divide inside opposite. We're going to divide x values by b. And in this case, it's the opposite. If b is bigger than 1, it's actually a horizontal shrink because you're dividing by a big number. You're dividing by 5, you get smaller. If b is less than 1, think about you have something and you divide it by a fraction. What happens there is you multiply by reciprocal, you actually get bigger. When you divide by a small fraction, you get bigger. It's a horizontal stretch. Best way to show you, let's go back to Desmos. In this case, let me put something in parentheses. Parentheses 3x. What do we say? Inside opposites, we're going to divide all our x's by 3. 1 divided by 3, it hits at a third of that. Right here. At 1, it hits at 1/2. It's a horizontal shrink. If I put a small number there, it makes it a lot bigger. Makes it wide. You multiply your x by y. 5, it stretches it out. You might notice that horizontal stretch is awful lot like a vertical shrink. They're the same thing. Let's say I put x squared right there. That's a horizontal shrink. It makes it horizontally smaller. It goes from here horizontally, makes it smaller. It's the same thing as a vertical stretch. Let's say I simplify that out. I just square everything. I get 9 equals 9x squared. Exact same graph. It's the same thing as a vertical stretch. In this case, I have a vertical stretch, which makes it skinnier, or I can have horizontal shrink. Same thing. I also call it dilation. Let's do some examples real quick. Now this one's easy. With these, is don't overthink it. Graph it like normal. There's that. My slope is 3/5. You go up 3, over 5, and you get your graph. Now with the next one, let's actually try. First, let me put a grid on here. Look what's going on with this one. First, notice that's on the outside. Outside, y follow. That means it's a vertical stretch. Vert stretch. Right, if we're doing a normal graph, it would be it's a parabola. Start here, across that 1, 1. This crosses that 1, 1. It jumps out from there. Now this one, the best way to think about it is the slope. You can start that from the very beginning. We're going to go right 1, up 3. Now it's not exactly slope. It doesn't follow it after this, but it's a good way to start off your graph. 1, 3, and it goes like this. You can see there's a little bit of a vertical stretch, thinner than it normally is. Vertical stretch of factor 3. That's how you do it. Application problem. Manager of a coffee shop is randomly checking coffee drinks prepared by employees to ensure the correct amount of coffee is in each cup. For each 12-ounce drink should contain half coffee and half steamed milk. The amount of coffee by which each drink varies can be represented by this equation there. Describe transformations in the function. All I want to do is describe what it looks like, and then we're going to graph it real quick. This is on the inside. Inside opposite, inside x opposite. Inside x tells me it's moved left and right, and opposite means the opposite of that. So it's a -12, we're going to treat it like a +12. We move it right 12. You can say shift right 12 or just move it right 12 units. And then the 1/2 here, notice that's on the outside. This is on the outside y follow. Y tells me it moves up and down, and we're multiplying with a stretch. We're going to stretch it. Actually, in this case, it's less than 1. We're going to shrink. It's a vertical shrink. We're going to shrink it by 1/2, and we're going to move it right 12 units. Now, if I want to graph it, we'll do a very basic, quick one. To move it right 12, and then This one you can actually do the slope. We'll go up 1 over 2. Up 1 over 2. Look like this. There we go. We want to write equation for each one. First key is understand what the parent function is. This is a parabola. We're going to write y equals x squared. That's what it basically looks like. What's going on is it's moving up, down, left, or right. Looks like it's moving up 1. If you move up and down, it goes on the outside. I'm going to write in like this. On the outside, I put plus 1. That's that equation. Over here, this is an absolute value graph, something like this. But in this case, we're moving it left 3. When we move left and right, that goes on the inside. Inside x opposite. I'm going to put an inside. Now also we have to make the opposite. Instead of a minus 3, we have to put plus 3 here. And that's what it looks like. So this one, probably the best thing to do is find the vertex right here. It looks like -4 and -6. So lets me know it moved left 4 and we moved down 6. Our base graph looks like this. On the inside, I gotta move it inside x opposite. This is why most people mess up. A lot of people give me this. I see this all the time for inside. That is wrong. The square has to be on the outside right there. So the way you want to write this is y equals x inside opposite plus 4, close it, and then put the square. And then out here we went down 4, outside y follow. So on the outside we're going to put -6, we fall on the outside. That's what it should look like. And that's the lesson.